In this video, I would like to talk about probabilistic constrained model predictive control for linear discrete time systems with additive stochastic disturbances. Model predictive control, called MPC, is a kind of optimal feedback control. The current control input is determined by solving a finite horizon open-loop optimal control problem, using the current state of the system as the initial state. This optimization yields an optimal control input sequence, and the first control input in this sequence is applied to the system at the current time. Moreover, this control procedure is repeated at each sampling time. An important advantage of MPC is its ability to deal with constraints on control inputs and states. In fact, constraints can be classified into two categories. One is the so-called hard constraints that must be satisfied with probability 1. The other one is the so-called soft constraints that cannot be satisfied surely, but satisfied with a given probability less than 1. Several MPC schemes have been proposed to fulfill these constraints in the presence of uncertain disturbances. Here, MPC method can be classified into two categories. The deterministic MPC that deals with hard constraints and the stochastic MPC that deals with soft constraints. In the deterministic setting, uncertain disturbances must be bounded, and most studies are based on the min-max approach. In this approach, a performance index is minimized over the worst possible disturbance realization. Therefore, the control performance is often too conservative, because no statistical properties of the disturbance are considered. It is known that a small relaxation of the probability requirement sometimes can lead to a significant improvement in the achievable control performance. However, probabilistic constraints are generally intractable in an optimization problem. In recent decades, much attention has been paid to this difficulty of the stochastic MPC problem. Thus, several methods have been proposed to handle probabilistic constraints. However, so far proposed methods impose some restrictive assumptions on uncertain disturbances as shown here. Normal Gaussian distribution, known in time invariant probabilistic distribution. These assumptions seem to be restrictive. Therefore, in this study, we propose a method that can be applied for arbitrary, unknown and time-variant probabilistic distribution. Note that restrictive assumptions in the previous studies are considerably relaxed in this study. However, in this study, the expectation and variance of disturbances are assumed to be known. So, the objective of this study is to propose a design method of stochastic MPC for linear discrete time systems under the assumptions that uncertain disturbances are random variables with arbitrary, unknown and time-variant probabilistic distribution. I would like to provide feasibility and stability conditions for this problem. Next, I would like to introduce some notations and system model. In this talk, the inequality, modulus, square root and multiplication are applied component-wisely. The notation at the blue underline indicates the positive definite matrix. Norms are defined as shown here. Moreover, the expectation, variance and covariance are defined as shown here. In this study, we consider linear discrete time systems described as shown here. X is the state, U is the control input and W is the stochastic disturbance. Here, we assume that all random variables are independent, and the expectation and variance of W are assumed to be known for every time. Here, let me show a motivative example. Generator dynamics in smart grid systems can be described by this equation. Here, W is considered as the renewable energy. Its behavior is uncertain, but we can estimate its expectation and variance. So, this is a motivative example to consider the stochastic MPC problem. Next, let me introduce the stability definition. The system is said to be almost surely asymptotically stable in the mean if this condition is satisfied. In order to consider the asymptotic stability in the mean at the origin of the system, we impose this assumption. There exists a positive real constant delta such that this condition is satisfied. Note that the disturbance W itself may be unbounded, but the expectation of W should be bounded and converge to 0 as the expectation of X goes to 0. Next, I would like to formulate the stochastic MPC problem. Here, we introduce the performance index defined like this. P, Q and R are positive definite matrices. FAI is the terminal cost function, and L is the stage cost function. Then, let xmin and xmax denote the lower and upper bounds of X. let P denote the probability in the vector form. Now, we impose the probabilistic state constraint on the optimization problem. So, the problem of stochastic MPC is to decide the control input such that the performance index is minimized subject to this constraint. Here, we introduce the augmented matrices defined as shown here. Then, the expectation and variance of the state over the prediction horizon can be described as shown here. Then, the performance index can be rewritten as shown here. Noting that the covariance is independent of U and substituting this covariance term into the term in the performance index, and neglecting the terms that don't contain U, we can obtain the relation to be shown in the next slide. Note that the minimization problem of J has been reduced to the quadratic programming with respect to U. However, in general, it is not straightforward to solve the quadratic programming with probabilistic constraints. So, L would like to show a tractable method for dealing with the probabilistic constraint in the next slide. Suppose that this deterministic constraint on the control input is satisfied, where U min, U max and kappa are defined as shown here. Then, this probabilistic constraint on the state is satisfied. This is a main contribution of this study. Therefore, the minimization problem subject to probabilistic constraint can be reduced to the minimization problem subject to deterministic constraint that can be solved using a conventional algorithm. Let me show a sketch of proof. This is a lemma that shows Chebyshev's inequality. For a given random variable W with a mean mu and variance sigma, this inequality holds true. This inequality is called Chebyshev's inequality. Using this Chebyshev's inequality, we obtain this relation. Here, this inequality can be decomposed as the one enclosed green line. Then, substituting these relations enclosed red line into these terms enclosed green line, we can obtain the deterministic inequality shown in the main theorem. Hence, we can state if the deterministic inequality is satisfied, then the probabilistic inequality shown in the main theorem is also satisfied. This is the outline of the proof of the main theorem. Next, I would like to show a stability condition of the closed-loop system with the stochastic MPC. P, Q, and R are weighting coefficient matrices in the performance index. Let C and G be defined as shown here. Now, we can state this theorem. The closed-loop system with the stochastic MPC is almost surely asymptotically stable in the mean, if there exists C and G such that this linear matrix inequality is satisfied. It is well known that the terminal cost function should be chosen as a Lyapunov function satisfying this inequality in order to guarantee the asymptotic stability of the closed-loop system with MPC. So, there exists a restriction on the choice of the performance index in order to guarantee the asymptotic stability of the closed-loop system with MPC. In fact, under several assumptions, we can show that if this LMI is satisfied, then this inequality is also satisfied. The detailed proof can be found in the paper published in IEEE CDC. Next, I would like to show the results of numerical simulations. Here, we consider a system whose coefficients are given as shown here. And other parameters employed in numerical simulations are also shown here. First, we consider two cases. In the case 1, we chose weighting coefficients P, Q, R as shown here. In this case, LMI stability condition is not satisfied. Namely, the stability of the closed-loop system is not guaranteed. In the case 2, we chose P, Q, R so as to satisfy the LMI stability condition. In this case, we can guarantee the stability of the closed-loop system with MPC. For each case, we furthermore consider two cases. One is the nominal MPC and the other one is the stochastic MPC. Nominal MPC means the MPC without the probabilistic state constraints. Stochastic MPC means the MPC subject to the probabilistic state constraints. So, we performed numerical simulations for 4 cases. Left figures show the time responses for the case 1-1. We can see that the system is not almost surely asymptotically stable in the mean. Right figures show the time responses for the case 1-2. Even if the asymptotic stability is also not guaranteed for this case, the performance is better than the case 1-1. So, we can see that probabilistic state constraints work well. In both the case 2-1 and the case 2-2, LMI stability condition is satisfied. Therefore, we can see that both systems are almost surely asymptotically stable in the mean. From these figures, it is difficult to find the difference of the performance between nominal MPC and stochastic MPC. So, I would like to show the variance for each case in the next slide. This figure shows the time response of the variance norm. The variance of the state in the case 2-2 is reduced better than any other cases. Consequently, we can verify the effectiveness of the proposed method by numerical simulations. Finally, let me summarize my talk. In this study, we considered the stochastic MPC problem for linear discrete time systems under stochastic disturbances. It was shown that the optimization problem subject to probabilistic constraint can be reduced to the quadratic programming subject to deterministic constraint. Chebyshev's inequality was applied to successfully handle probabilistic constraint with less computational load. Sufficient conditions for the stability of the closed-loop system with stochastic MPC was established. Consequently, the stochastic MPC method was successfully established for linear discrete time systems. That's it. Thank you for your attention.